Thanks, Tom, for this great introduction. Thank you very much. Hello, everyone. Very nice to be here. Thank you for the invitation and to be able to share our technology with you. So today we're going to discuss oxide reduction, cementation. We believe it's not over, and our motto is essentially scavenge, clean, and monetize. I'm Guillaume Lefort, the CEO of Cleanmetals. And obviously, as you can see, this is clearly not us at all. We wanted exactly to make that point, but this man is a revolutionary person, and we are an evolutionary company. What we have done is essentially take something that has been existing for a very long time, and we've morphed it into something modern, such as the windmill became the wind farm. I'm not going to teach you what cementation is. I think everyone in this seminar understands cementation very well. It's essentially the natural reaction of ion exchange between a reductor and an oxidating metal. In most of the presentation, I will use copper as an example. It's an easily cementable metal and one with which we have a lot of experience. So this essentially what you see here on the screen is the industrial cementation reactor that we have engineered and developed. The reactor is approximately 3 meters high and has we treat a nominal flow of 25 cubic meters per hour. And inside the reactor, you have a fluidized bed of iron shots, which are 1 to 2 millimeters in diameter. This fluidized bed of iron shots essentially acts as an increased surface of contact area for the metal that needs to be cemented. The metal that needs to be cemented goes through the bottom of the reactor. I'll show you in a second a little animation, and goes inside the fluidized bed. So let's see the animation here. Thank you. So I think this has given you sort of an idea of how the reactor works. So if I go back into the reactor, as you know, as I told you earlier, the wastewater or the PLS, whatever we need to treat, comes through the bottom of the reactor and goes through the fluidized bed here. One of the key areas that we've focused on clearly is how do we create a substantially larger surface area, and how do we regenerate that surface area to have a totally dynamic and totally optimized cementation process. We use ultrasounds, and essentially these ultrasounds allow for the separation of the cemented copper on top of the iron shot, and therefore regenerates the iron shot, so it's always available for cementation. So unlike other cementation processes, where you would have a very static dynamic, This doesn't happen here. Everything's in movement all the time, which allows us to have very high kinetics. And we've had extraction rates higher than 95% with different types of PLS, as low as 0.3 grams per liter of copper and as high as 20 grams per liter of copper. So I'm going to move on from this one. Here you can very clearly see what I mentioned a bit earlier in this second photo, in the photograph, which is a photograph from a microscope. You can see the copper that has been separated and liberated from the iron shot. And that's very, very visible. And essentially, this is what I explained earlier. It gives us the kinetics and the whole system gives us a very pure powder copper. So what it does is essentially we have ultra fast kinetics, a totally automated equipment. We control the reaction, so we can do a lot of stuff with regards to selectivity also, which I'll speak of in a second. And we have a low iron consumption and a pure output. Okay. So these are essentially 3 photographs that are taken within 11 seconds of one another. You can recognize on the left the PLS, which has just started to run through the reactor. It's still very turquoise, nothing has really happened yet. Then very quickly you can see this is starting to turn a bit brownish, where we start having a copper cementation reaction. And very quickly, within 10 to 11 seconds, you can see how much metal is cemented, how much copper is cemented from the fluidized bed. Okay, so this is again the power of the kinetics. We've got to extraction rates. As I mentioned to you, we've always been above 95%, but we can change that. If, for instance, we wanted to have a 60% extraction rate because we don't want to cement something else, or because we want to leave a part of the copper or other metals afterwards, we can actually reduce the residence time in order for this to happen. So this is totally doable, and it could be something to be done in impurity management, for example. The 25 cubic meter implies that we're going to produce 17 tons of metal per month at 1 gram per liter. 2 grams per liter, 34 tons, 3 grams, 51 tons, and you go we manage the nominal flow as I mentioned earlier. So low and controlled OPEX and a high sell price of the end product. We're essentially close to LME in all what we've produced in the past. This is the launch of a reactor that we have on one of our pilots, which we did a measurement that we did, which is an 18 cubic meter reactor, a bit different from the one I showed you. And you can see here it's very interesting, but within 40 seconds, we were already at 98% extraction rate. And interestingly, this was in a piloting that we made with also a lot of arsenic content. So the cementation of the copper didn't change, and it worked perfectly well. So that shows you the power of the kinetics, again, the power of the fluidized bed. So I mentioned earlier selectivity, which you cannot do with other types of cementation processes because the reaction is too slow. So, and you can't really control the parameters. So you find yourself with cementing everything that's more or less in the source, which you don't want to do in certain cases. Now, I'm not going to be too technical on this. There's many iterations that we could go into, but I think the most telling story is we were working with some clients which had an 80-ish% extraction rates on their cementation and a lot of arsenic content in their feed. A lot of arsenic in their feed, of course, but also a very high arsenic content in the cement, the end product. So what we managed to do is very quickly, we increased the extraction rate by 15 points and we're around 97%. But more importantly, we really managed to reduce the arsenic content in the cement, in the copper cement as an output, which transformed a toxic product into a product which became totally sellable within the REACH limits, okay, because the REACH is less than 1,000 ppm of arsenic. And this, I think, exemplifies very well, this simple example, for me, certainly speaks of the power of the reactor and the power of our cementation process. I think that we can do different types of selectivity, but we're not going to get into that all today. This is typically a production of copper. So you have the reactor photograph you've seen before. We do the ion exchange. We produce the copper metal. We have a filter press. You can see a beautiful sort of copper there, which is into the filter press. Then we discharge the filter press. Sort of we crush it to get this powder copper, which we put in big bags and we sell. There's direct applications for our copper cement within the fertilizer industry. It can be put back in the smelter. It can be, many things can happen to it, but we also have direct applications because it's a very soluble material for industrial users also. So sometimes they really like that. With regards to operations, so there's no moving parts. The only moving part would be the pumps, but pumps, you know, doesn't, if you're well organized, you're going to make sure that you don't have downtime if you have a pump issue. It's a very versatile tool. They can work in batch and continuous. We don't need to change the equipment for different solutions, and there can be, we can treat any type of solution coming to us. We can change some parameters if need be, but say you have one day a 3 gram per liter solution and the other day it's a 1 gram per liter solution, it has absolutely no impact on operations. We would just consume more iron, and that would be the only impact. We need to accelerate the iron feed. A very compact footprint, so we're very much a plug-in operation, and we have, as we said earlier, a low iron consumption, which is good in terms of cost, and it's also good in terms of discharge on the back end. So there you go. That's the sort of operational strengths of the reactor, we would say. Now, regards, and that's probably very interesting for you as students and researchers and academics. Here you have a periodic table with the metals with which we work. Now, the gray metals are what we can use as consumable. The orange metals are the metals with whom we have already worked. And the blue metals is metals with whom our technology would work, but we have not yet been exposed to them. So there's, you know, a case in point, if you knew of some blue metals that we could actually try the technology for, you know, it could be very interesting, certainly to us and perhaps some of your colleagues, clients, or other. So we've worked chromium-6, which we transformed into an alloy of ferrochromium-3, an oxide of ferrochromium, sorry, nickel, copper, arsenic, obviously, as I mentioned, lead, indium, cadmium, and rhenium. That's the exposure we've had up to now. We unfortunately had won a tender offer with Nornickel, and we're supposed to work also with palladium, silver, gold. What else? Palladium, silver, gold, and cobalt. But unfortunately, with the events of last year, that couldn't materialize, so we didn't do that. These are different applications. I think I'm not going to go into too much details here. There's so many applications, providing it's an aqueous solution with a pH negative, not negative, but a pH from 0 to 4. We can essentially work in any kind of situation. And recover any kind of metal with whom the physics of the cementation would work. And then we need to adapt some parameters, but there's nothing fundamental to do. The reactors would be the same. So I think, you know, if you've asked yourself a few of these questions, clearly, you know, how can I treat 25 cubic meter PLS at a gram of copper economically without investing a massive amount of capex to do an electrowinning plant? Then we are an answer to that. How can I treat 100 cubic meter with a substantially lower copper? How can I value metals in my wastewater? How can I reduce my iron content in my cement for current operations, which would be fairly polluted by iron? How could I fully automatize the process? How can I selectively extract metal from certain PLS? You know, I have a limited amount of resource. I don't want to invest a stupid amount of capex in an operation that's going to be complex and which is going to have a small output. Well, perhaps we're the perfect tool for that. So that's it's typically for existing operations. I only have a recovery of 80%. How can I go to 95%? So these are typically the kind of a question someone who is looking at a copper, certainly a copper dynamic, would ask himself. Clearly with nickel, because of the value of nickel is substantially higher, the economics are even better with even lower grade solutions. So this is an example where we can make a strong difference of a smelter which loses 100 tons per annum. Now, it's not much, but 100 ton essentially is 3,000 price, the copper of 3,000 price. And I think this is a general message of what we do, is we're not here to revolutionize everything. We're not here to fundamentally change the mining industry. We are an optimizing tool that is here to be used in cases where you don't have an appropriate technology to recover lost metals. So we don't aim to be anything else. This is our thing, and we're very good at it, and that's what we're focusing on. And with this kind of message, we view there's a lot of metals to recover all around the world, and this is where we want to do all our installations and plugins. So here is an interesting example, which was an existing site in Chuquicamata in Chile. That is on top of a now subterranean mine, and they needed to get rid of the water. Now, the water had a pH of approximately, I think if my memory is correct, it was approximately 1 or 2, and it had 1.5 grams of copper per liter. So it was essentially the total sweet spot for us. We essentially put a pump in, pump it out, and produce the metal. Now, obviously, this never happened. Why didn't it never happen? Because the mining industry did not want to actually do something fundamentally with this. There were options. It was fairly easy to take the copper out, to pump it, and then neutralize the water and put it back into the system. And what actually happened is that the water was pumped out and put in the air and then essentially evaporated. So all the ionic copper was also put on the ground. This is how this was dealt with. Rather than pump it, produce the copper, and neutralize the water correctly. Now, this is in an area where everyone's lacking water for operations, okay? And yet, no one was doing the right thing. And there's quite a few of these stories which we think right now are not really acceptable, and we need to evolve into something more sustainable, okay? So, you know, essentially, conclusion, scavenge, clean, monetize, scavenge some more. This guy will certainly need a lot of nickel and copper to put in all his cars and all the batteries we're working for. So, you know, if you have any ideas for us, or if we can help you in any kind of recovery, give us a buzz. And don't forget, you know, we have all these metals everywhere. Recycling is exploding, and we need essentially to make sure that we don't lose any of the resources, because unlike oil, which is consumed, most metal can be reused, and we need to make sure we recover what is produced, what is not produced, and left behind and recycled completely. So that's what we're aiming towards, and that's what we're working for. I think I would add a last concluding point, perhaps, which doesn't come out necessarily in everyone's mind straight away. The main reason why our tool is fundamentally interesting economically is that we consume a function of what we produce. Therefore, the nominal charge of electrowinning plant is running all the time. It needs to be concentrated to have a price per output per ton, which is controlled. In our case, we're only going to consume the iron, but we're going to function of the copper we're going to produce. And I think that's very important, and that's why we're very strong on very low concentrations. So I think that concludes my presentation. I think, I don't know, Tom, or if there's questions and we want to open to people, and have questions specific on certain slides or more generally, I'd obviously be absolutely delighted to answer everyone or to listen to any comments.
Oh, thank you very much, Guillaume. That was fascinating. Yeah, we'll throw the open the floor to questions and online questions. If you want to raise your hand through the Zoom app or type a question into the Q&A box, then please go ahead. Do we have any questions here? Well, I have one to kick things off, Guillaume. Do you have any idea of, you showed figures for the potential copper waste from one particular smelter and potentially recovering 108 tons of copper per year, which is a pretty substantial amount. Do you have any idea globally what the potential amount of copper that could be recovered through smelters and process plants and what have you around the world? Is there sort of a big order of magnitude arm wavy picture of how much copper is there to be had through this and other technologies?
So it's very difficult. So I'm going to answer two ways. The first, we have a pipeline where the amounts are really massive. To be honest, I would need to review exactly what we're talking about. But it's actually a fairly difficult one to address the market because it's not something industrials are happy to let you know about. So it's not shared or public information. You will have discharge elements. If you look in many countries, you have discharge or what's being left out of it. But sometimes you don't have the full information, and it's fairly difficult to actually get a global view on that. What we do know is that everyone we've spoken to who has not yet taken a decision has not sorted out the solution. And that's, a lot of people. And there's all the other guys we haven't spoken to. So there is a lot. And I think the message is that we need to get it out because it's lost otherwise. If you precipitate it as part of a final operation of wastewater management, you precipitate everything together to clean the water, you're losing the metal. This is going to go in discharge and landfill, and that's never coming back.
Excellent, thank you. We have some questions coming in online now, and the first one from Guy Butcher. Can Guillaume please advise the scalability of the ELSA reactor, i.e. are there plans for larger capacity columns?
So as of yet, there are no plans, Guy. The main reason is while we have produced 1,000 tons of metals and we consider ourselves totally TRL9, the industry does not see it yet as a validated technology. And therefore, as we have a 25 cubic meter reactor, but it works absolutely beautifully now, I do not want to invest into a larger scale reactor for now. We want to install these first, get going, and once the industry accepts, but we're a reliable partner, then we might look at that. But it changes, we have we can have up to a ton of iron into the reactor. So if we were to increase the size, it will change also the strengths elements and all that, which is not a mean feat to go into. So we're sticking to 25 cubic meter for now. And if we need to treat 50 cubic meter, we'll just put 2 reactors.
We have another online question here from Nicholas Clark. Are you able to recover metals sequentially if they are present in the same solution? For example, copper and nickel cobalt.
So yes, the answer is absolutely we are, but we would need to do a filtration to recover the first metal that's cemented so it doesn't pollute the second cementation reaction. So what you would have is a reactor, a filter press to recover, say the copper, and then we would align change a bit some parameters, and then recover the nickel and the cobalt, which we've never had in solution together. We have actually never dealt with cobalt yet, but which are very close. So we anticipate that they would come together quite quickly. So we don't know how we can selectively separate these two, but with the copper and nickel, nickel cobalt is extremely easy for us. So the answer is yes. And it could also be done in the same reactor. Say you had 100 cubic meter to treat per day. We could treat the copper for 4 hours and then put it through the filter press and get the copper out and then put the nickel and cobalt in the same reactor with the same fluidized bed. That's not a problem at all.
And we have a question from the lecture theatre now. This is Nick Cook.
So it was interesting to see the arsenic separation. So where was that actually going, and what was the material that you recover the arsenic into to take it out of the solution? Because, I mean, we all know that, say, copper, nickel, PGE systems, and sometimes some of those sorts of things have lots of arsenic. So if you could actually head down this route with cobalt, arsenic, copper, nickel, it would be fascinating. But where was the arsenic actually going in the process?
Well, the arsenic was staying in solution. And that was a trick, is the arsenic prior to what we were doing was essentially being cemented with the copper and created this difficult to sell, if not impossible to sell product, unless you mixed it with another cement. In the case, so we were really leaving it in solution. That was the trick. Now, arsenic cements very well. We could have cemented it also if the client wanted us to, and it works very well. But it's better to do it obviously after the copper. So that would be, comes back to the previous question, we would do it in 2 stages, okay? So that's for that. With regards to your comment on the arsenic and the cobalt, arsenic would cement prior to cobalt. So it would be, we could clean up, if you had a solution with some arsenic and cobalt nickel, then we would probably get rid of the arsenic before, and you would have a clean solution, just with the pollution of the iron that we would add in the solution, which very often is already there in a certain quantity in any case. So say you have a gram per liter of arsenic and you have 20 grams of iron, you would have a solution with 21 grams of iron, 22 grams of iron, and then your nickel and your cobalt. I hope, does that answer your question, sir?
That's a nod.
Okay.
And we have one more question from online. An anonymous viewer has asked, do the iron beads rust and affect the product, or are they stainless steel?
They don't rust. They don't, I mean, I mean, if we left them, they probably could rust. But they're, you know, when they arrive, they're essentially put in, we get them in big bags and they're fed in the reactor. So there's no rusting of the iron beads. And they would, and in any case, now let's go the extra mile of the answer, because we work in very low pHs. If they were to rust a bit, as soon as they enter the reactor and get a fluidized bed, we would get rid of that extremely quickly. So not an issue.
Excellent. One more question on the floor.
Sorry, I might have missed in your presentation the extraction at Chuquicamata. What was the total value of copper that was recovered from that water at the bottom of the pit?
Nothing was, unfortunately, that's the trick. Nothing was recovered. What I was showing that is, you know, to show the idiosyncrasies that sometimes our industry is faced with. The water was essentially pulverized over the desert and all the copper with it. There was 1,500 tons of copper to recover and 1 million tons of water, 1 million tons of cubic meters. But they didn't treat it correctly. So our call on this essentially is say, well, in this case, it wasn't much copper, but what we say, well, all things considered, what we say is we can subsidize the water treatment for you at no cost, essentially by recovering the copper.
Yeah.
And therefore, you recover that. It's a great ESG message. You recover water and you put it back. So talking about circularity, this is a perfect example of what should be done. And some of you will know, and that's no secret, you know, in northern Chile, the cost of a cubic meter of water now, but there's no water, it's all desalinated water, which is pumped up to 3,000 or up to 4,500 meters. I mean, we're talking up to $10 a cubic meter. It's not nothing.
Yeah.
So recovering water and for us to be able to subsidize a treatment, a water treatment and neutralization or different things, I view as very important as part of what we're all trying to achieve, which is more security and optimization.
Second question, if the water has already a very, very high iron content and iron cycle, how does that affect this process?
So we've worked with the answer, and I would like to have one of my engineers on here, but they're sleeping. But the answer would be that we've worked with very high iron content already. And when I say that, I'm talking, you know, 80 grams, 85, 90 grams. And providing we stay in pHs which are lower than 3 in that, we don't have any issues whatsoever. What can happen when we go in pHs which are a bit higher is that we find ourselves with a production of hydroxides of iron, and that can be it's not a fundamental recovery problem, but it becomes a filtration problem. So that needs to be managed on top. But it essentially, you know, up to 100 grams per liter, we haven't seen any problems. I hope that answers your question. We
have 2 related questions now online. from Craig Brown and an anonymous attendee asking about the cost of the iron shot. Craig has asked specifically, could you comment on the price differential of iron shot versus scrap iron?
So, very good question. The scrap iron, first of all, there's different markets in the world. So I would say the first answer is, it really depends where you physically are. So then we enter, there's a little nuance in the iron shot. I can have iron shot tomorrow at 700 tons, $700 a ton. And I can have the ones at $1,200 a ton. Now, the question then for a user is, which one does he want? The one that is produced in China at extremely high CO2 ton, or the one which is produced in other places, which has a low CO2 footprint and therefore a low copper recovery CO2 footprint. So that's essentially going to be the range of prices. But essentially we use $900 to $1,000 per ton when we speak to our clients, but we can do better if need be. Yeah, that's the answer. It's a manufactured product. What you would tend to see is that the increased one important actually element in this answer for the gentleman or the lady who asked is that generally the increase in recovery, the better product and the lower consumption of iron totally pays many times for the increased cost of the iron of a manufactured product we use relative to the scrap iron. So that's never really an issue when you look at the numbers on a global basis.
Well, that's all the questions we... Oh no, one more question from the floor. Oh.
Thanks, Tom. Evening, Guillaume. It's Katerina speaking. Fantastic presentation. Thank you. My question is probably very broad, and I'm just wondering if you could touch on some of the issues of the technology, or where to from now. So sort of like what's some of the improvements you would like to make, or you know what I mean? Like what other innovations could really, really help you?
So I think, you know, and I don't want to sound arrogant here, but I think on the innovation with regards to our technology, we're already running at 97% extraction rates. We can do selectivity of what we've been exposed to. So I don't think the hardware needs any improvement. What we do need to increase is, first of all, we need to install plants, and we need to get going on that. We have quite a few places where we can go to now, but it needs to happen because there's been a lot of talk. We're very close many times, but it didn't happen for many, many reasons, which are not good. It's too long to enter because you can imagine the length of time it takes to get to decisions. So I think next is we really need to get going on installing plants. And what we do need to get going, which I think answers your question in a different way, is we need to get more exposure to metals we haven't worked with, because perhaps we can do a lot of stuff which we don't even know about. So I think it's not so much the hardware and the development of the technology. I think it's getting exposure to different types of PLS with, you know, I don't know, vanadium, scandium, cobalt, nickel, more nickel, which would actually put us in a situation where we can actually create perhaps a specific application which we don't yet know about. I think it's more in this dynamic, Katerina, but I think we need to ramp our game up. And clearly, obviously, with people like you and academics, we'll have ideas who know all the processes well. We'll have ideas actually, oh, by the way, I think about it, you guys should look at this. And then we can perhaps look at with clients. But I think on the hardware itself, you know, we have a low consumption of iron, or approximately 1.1 to 1. We have extremely high recovery rates. We have a good quality product. So I think there's not really much to do on that side. It's very marginal. Whatever we could do would be very marginal. I think it's really exposure, commercial exposure, operating exposure, and obviously new types of new types of PLS which we don't know. Obviously, in Chile, we're becoming quite masters of the arsenic element. We're working on another very, very complex pilot campaign. And we'll see where that goes. But yeah, so I think that's the answer. And the one thing I would say is when we talk about a pilot campaign at Cleanmetals, it's not with regards to validating the technology. It's with regards to trying out a PLS, which is complex, with our pilot in order to better understand it and be able to tell to the client quite affirmatively, this is what we can do, this is how we're going to do it, and this is going to be your OPEX and your CAPEX. It's not a pilot, and obviously to demonstrate to the client so they can integrate us in their flow chart, because if they don't see it, they won't do that. But there is no research from our side with regards to the hardware. It's really how do we calibrate the hardware in order to be able to do this? I think that's really the important thing. Have I answered your question, Katerina?
Yes, thank you. Well, no more questions online or on the floor. So coming up next week in the seminar series, we have David A. Isidon, the co-founder and technical director of Ballymore Resources, talking about opportunities and challenges in redeveloping historic high-grade mines in North Queensland. I hope you'll join us again for that one next week. But please, can you join me in thanking Guillaume Lefort one more time?